Oh, welcome back, everyone. We're going now into our time domain science section for the workshop, and the next two lectures and the tutorial is going to be presented by Marissa. Now, Marissa completed her undergraduate and master's studies in theoretical physics at Stellenbosch University. And although her masters were actually a very theoretical project at its core, it did have an astrophysics theme. And it sort of got her interested in SK. When she was doing her PhD in Oxford, she did it in pulsar scattering, and it ended up she got hooked on the challenges of astronomy and processing astronomy data. So as a consequence, Marissa now is a commissioning science for the MeerKAT telescope, part of the team here. Her research undertakings at the moment include, as a member of the pulsar timing and searching projects on MeerKAT, she has to investigate giant pulses from young energetic pulsars, fast radio bursts, understanding the interstellar medium through pulsar analysis, and the timing of relativistic binary pulsar systems. Marissa, please enlighten us.
Hi, Ruby. Thank you for that lovely introduction. I hope everybody can hear me. I'm sure you'll tell me otherwise. So from my end, also just a very welcome to all the students attending this African Winter Radio Interferometry School. And in particular, my thanks to Ruby and the team for giving us this section in the school on time domain astronomy. I'm absolutely delighted that we'll have the rest of today to dig into this field. And I suspect for many of you, it will kind of be a first introduction to time domain astronomy. And so during this lecture and during the next lecture, you will learn that the main targets for time domain astronomy are pulsars, but there's also these objects that we call fast radio bursts that I'll briefly touch upon. So I'll try and use the term rapid time domain to kind of capture the whole group of things that happen at high time rates. And so you would have also received an email from Ruby this morning, passing on some details for a pulsar timing workshop. So first, I'd like to say that in South Africa and Africa across this sort of rapid time domain and pulsar astronomy community is very, very small. And MeerKAT is an absolutely fantastic instrument to do this type of work with. And so I'm really encouraging students that are keen on what they learned today to get in touch with me and to look out. I'll give more information about the pulsar timing workshop that we'll be hosting at the end of the tutorial, and you also have the form in your inbox already. So please be in touch if you're keen on this. For that reason, the lectures will also be quite introductory in nature today. So I know you've done some very advanced and technical interferometry work, but for today, I'd like to also give exposure to maybe some of the younger students in the audience who are still developing their interests in astronomy, and I would like to expose them to these other options that we also have apart from image domain work. So that was my introduction. Let's get started. I suspect by now you're seeing the opening slide, and let me just get my slides switching going. So these are basically the points we're going to try and cover today. So first, I just want to give you a feel for what I mean by time domain astronomy and how that is different from image domain astronomy. And then we'll look at, and I'll briefly mention the sources, the pulsars and the fast radio bursts that are the main targets for this type of astronomy. And then once you've got a better feel for that, we're going to look at the process of creating a phased array, which is what we need to be able to observe these sources. And that's where the process of beamforming fits in. And I'll give you some context as to how this fits into the MeerKAT signal chain that you've already learned about. And then before we can actually conclude the process of beamforming or forming the tide array beam, we have to make a quick detour back into the far field of astronomy and just look at the impact of the interstellar medium on our radio signals. And that knowledge might change how we do the last steps within our beamforming process. And then I'll just end the lecture here with a discussion on how this type of science also needs timing support in the forms of atomic clock and accurate timing, accurate timestamps at the telescope to ensure that we can actually extract valuable science. Okay, so let's get started on this first bit. So I think if you look at the beauty of some of the radio astronomy images that you've probably come across in the school, the beauty can often lie in sort of these details that we see for the first time if you're using a very highly sensitive telescope such as MeerKAT. And so, there's my cursor on the move. Yeah, if you look at this MeerKAT galactic center images, the MeerKAT is so sensitive that for the first time we're seeing these sort of magnetic field line tracers and wisps and things we didn't know existed before. And in order to get to this level of sensitivity, well, you've learned there's basically two things going on. On the one hand side, you've built the interferometer such that you've got a great distribution of baselines, and so you're really getting high spatial resolution. And on the other hand side, you've built a sensitive instrument with a low system temperature, and so you're able to make these detailed maps. But lastly, even so, you still have to track the target field quite often for 8 hours or so to really build up this detail. And you don't really worry that while you're observing for 8 hours that this the subject of your interest is going to change much, because much of the sort of radio processes that we study can be quite slow, especially slow compared to the 8 hours that you are observing. But then on the other hand side, I'm sure you've heard this before, there are many astrophysical events that do change with time and have much shorter durations. So think, for example, of gamma ray bursts, during which vast amounts of energy are released on quite short timescales. Now, for such events, we actually want to track what is happening over time. How is this emission changing? And the whole collective of astrophysical events that are basically characterized by how they change at radio wavelengths is the so-called Radio Transient Sky. So what does the Radio Transient Sky consist of? Well, so like I said, gamma ray bursts, soft gamma repeaters. Think of bright supernovae explosions that you can track in the radio. And then things like radio jets coming from these active galactic nuclei, or from black holes and X-ray binary systems where you've got the black hole accreting and shooting off these incredible radio jets. So even so, for these processes, it will often be true that the radio part will sort of brighten or dim in days to weeks. So I've got a cartoon here of a gamma ray outburst, and so the gamma ray is the emission from the outburst is propagating, and you've got all this prompt emission at the high energy levels of the gamma rays, and it's really only here in the green arrow as part of the afterglow that you see the radio waves detected. And so we can still benefit from making images of this. We track them on sort of a cadence over which we expect them to brighten. So, for example, there's a project on MeerKAT called ThunderCAT, and they do weekly monitoring of X-ray binary sources for exactly this reason. And then moving on, is a subset of sources which just change so fast and on such different timescales that if we want to understand what's going on, we need to sample at a much higher timing rate. And like I've mentioned, the main source within this group of sort of rapid transients are pulsars. And so pulsars are very compact objects. They're point sources. So there's really also little point in imaging them with your advanced interferometer with its incredible baselines, because you won't be able to resolve the source. But if you can sample at a high enough rate, you can see the light curves coming in. So in this animation on the slide, you should see this neutron star spinning, and it's emitting this beamed radio emission. And I can't do anything with that in the image domain, but if I could sample the light curves fast enough, then I can basically see the signal. And the shape of the signal is where the interesting astrophysical information will live. And so they're also quite weak sources, so much weaker than these other supernova explosions or transient events I mentioned. And so in the next lectures, where we really look at what pulsars are and how we do the data analysis, you'll learn that we also have to sort of add these light curves together to be able to build enough signal to noise ratio to see these pulses. So as most animations, this one is oversimplifying the story a little. And then there's one other type of source for which we also use beamforming at the moment. So this is a very recently discovered class of objects. It was only discovered in 2007, and it's these types of discoveries that also encouraged me to talk quite broadly about things like rapid time domain radio transients, because who knows what else we could find if you keep on looking in these sort of regions that are less explored. And so the fast radio bursts were discovered because we already had the technology in place to look for pulsar signals, and they came in as these very short radio bursts. And what makes them quite different from pulsars is that from analyzing the pulse that they emit, you can infer how far you think this pulse has traveled. We'll look at these properties again later on. And we could tell from the pulses that were first discovered in 2007 that they were coming from cosmological distances, so they were extragalactic. And now to date, people have intensified their searches for these sort of very short, very bright, often once-off pulses. And there's up to about 100 in the online FRB catalog, and many more known that will still be added there. And MeerKAT has also found its first FRB. And Ben, who's going to speak to you later this afternoon, is quite involved in that type of work. And so FRBs are different from pulsars in that they're often once-off, which makes it seem like it must be some sort of catastrophic event, like an explosion. We still don't really understand the origin, but maybe like a collision of sorts. But some of them are observed to repeat. But when they repeat, it's not like pulsars that they rotate and you see a pulse every rotational period. They just seem to have these sort of seasons of flare-ups. So the most well-studied FRB probably emits like a bunch of bright pulses roughly every 5 months. And so understanding exactly what these things are is still an area of ongoing research. But the point here is that we wouldn't have found these things if we weren't looking at these incredibly high time resolution data. Okay, so why do we then use interferometry for pulsar astronomy? So I think much of this has been repeated across your lectures in the school, as that sort of the old school telescopes were all these large single dishes. And as you want to discover fainter and fainter objects, you need more and more collecting area. And finally, we've turned to interferometry. So the telescope that probably discovered the most pulsars historically is this Park 64-meter dish. And then there's also Jodrell Bank, which you may have heard of in the UK, Effelsberg in Germany, and as has been mentioned, this Arecibo dish that's no longer science operational. So the basic idea, even for rapid time domain astronomy, remains. You just want more collecting area. So this is a little MeerKAT cartoon from the mission MeerKAT cartoons. You can find them online, and the MeerKATs are just basically saying, yeah, if there's more than us, more of us, then we've got more eyes and we can see more and we can find more things. But later in this lecture, you'll also see that interferometry in some sense isn't really necessary for pulsar astronomy. We don't really need the long baselines, but we can do some other creative things with the fact that we have so many antennas to our exposure. All right, so that was kind of a brief introduction. Now we have to talk about what exactly is this phased array that we need to form for beamforming experiments, and how do we go about calibrating it. Okay, so luckily I know that this has also already been, you've already been introduced to this idea that when you've got an array of antennas on an interferometer, you can basically combine the signals of these antennas in two ways. And this depends kind of on your research of interest. So either you correlate the signals, as you've learned in the interferometry part of this winter school, and that leads to creating the fringe patterns, and ultimately, once you've done the imaging that you learned about yesterday, the sort of 2D spatial radio maps. But alternatively, you can also choose to add the signals from all the antennas coherently and in phase. And in this sense, we'll just use a sort of a stricter calibration measure to make sure that the array is phased up correctly. And I'll explain what I mean by that shortly. So once a phased array is achieved, you basically have a beam in the sky. And this beam will have maximal sensitivity to a small patch of the sky because you're going to use it to observe compact sources. But in this process of actually combining the signals from all the antennas, at some point you're going to detect the signals. So you're going to take the complex voltages, sum them, and ultimately square them to get the power out. And in this process of sort of detecting the signal or imputing the power, the phase information is lost. And basically, part of designing a beamformer is to decide at what point do you let go of this phase information. And we'll look at exactly how MeerKAT does this down the line in this lecture. And most modern day interferometers will hold on to this phase information a little longer than they previously used to. Okay, so here you are, just an interlude to remind you that you have actually learned of this coherent sum interferometer from Ben's lectures, and I think it's come up since again. Okay, so how do we calibrate this? So I'm going to call this sort of active precision calibration to form a phased array. And the reason I call this active is because you will see that many of the calibration procedures are similar to what you do for interferometry and how you calibrate your imaging data. But it's active for beamforming in the sense that we have to do all of this on the live system before we start our observing experiment. Because once we formed the beam and once somewhere down the line we square law detect the voltages, we will have lost the phase information. And so later on, you won't be able to just get rid of the contribution of a single antenna. So there's kind of two steps in MeerKAT. Doesn't necessarily have to be set up in this way, but the idea is that you start out with doing exactly what you did for image domain work. So you basically want to correct for all the geometric delays between the various antennas and add the signals received by them such that they are in phase at a predefined array center. So that's what my schematic is meant to illustrate here, is that you fix the delays between the different antennas such that everything that you add at this array center is in phase. And now, of course, geometric delays in MeerKAT isn't really the issue. We don't move the antennas around, so that's quite well understood. But it's the delays in the electronics that we have to correct for, and these will change over time and also with observing frequency. And so that's why they need to be calibrated every time you switch on the telescope. And so the way we do this calibration, as I'm sure you learned in the calibration lectures, was it yesterday or the day before? So this is basically the process of computing that Jones K matrix, right? So you first you observe a well-known bright point source, so something like a bright radio AGN that's in the far field, and you use the calibration solutions that you obtain from this observation to induce these phase shifts so that you know you are adding signals from each antenna correctly in phase at the array center. And you also have to do this independently for the two polarization streams like you learned yesterday. And this you can do by firing by injecting a polarized signal, a signal for which you know the polarization properties very well. And so in the MeerKAT case, that's the noise diode, and we fire the noise diode during this observation session. And from that, we can compute the delays that exist between the signal streams associated with the two polarizations for each antenna and correct for that. Okay, so that is quite similar to what you already learned yesterday. And then there's a second process of active calibration when we form a phased array. And again, you'll recognize many of these calibration matrices, the B and the G matrices, from your interferometry work. Here we just apply it before we actually even start the pulsar or the time domain observing session, because as I said, at some point we'll be adding signals in such a way that we can't reverse the process. So in reality, so I'm going to call the second step beam calibration, and this is where we will calibrate the band pass, the per-antenna gains, and the cross-polarization phase. In reality, this process starts by fine-tuning those geometric delays or electronic delays that you've already calibrated. So you compute some small correction to that to bring them even better in phase, if you will. And then thereafter, we correct for the differences in the bandpass shapes. So again, you'll be observing a well-known calibrator source. And as you're observing this calibrator source, you will have a flux model for this source, and you will basically normalize the bandpass shape for every antenna with respect to the spectrum that you know, the flux model that you have for the observed calibrator source. And so in this way, you are basically setting all the bandpass shapes for the antennas to be equal, in a sense, flattening them. And then you also apply these per antenna gain corrections that you've learned about, the sort of catch all G matrix corrections during this observing scan. And lastly, based on how the two polarization data streams differ, we also fix a phase offset between those polarizations. And just to repeat the essence of this idea, the reason we do these calibrations beforehand is simply that when we look at the signal chain, as we will in a bit, at some point we will do a square law detection, and we will not be able to, after the data is taken, say, oh, but M3 was being weird. You'd be stuck. That would be baked into your beam. Okay, so that's kind of a rough overview of what needs to be done in terms of calibrating the coherent beam. Here, I just want to show it in action. So if this in particular refers to having made sure that the bandpass shapes for each antenna is similar or equal as much as you can have them be. So here are two bandpass plots, one taken at L band at the top. So L band for MeerKAT, you've probably learned by now, runs across these frequencies from 800 up to about 1.7 gigahertz. And then U band is the receiver that operates at slightly lower frequencies, but has some overlap with L band, so from 500 megahertz up to about a gigahertz. And especially at in this U band plot, you can see it quite nicely. Left to right are essentially the same plots, just different sort of Y-scale power measurements. But you can see that after I applied that second beam calibration process, or a sub-process of which is ensuring that all the band passes are the same, you can see that they now lie quite neatly on top of one another. And similarly, there's a larger spread for L band, but it's much less than if it was not flattened in this way. And of course, you know by now that these peaks are associated with RFI, where the calibration solutions don't hold. Okay, so what does this tide array beam look like? So the idea of producing a calibrated phase array can also be said to say that you've produced a tide array beam. These are all different words for the same concept. And basically the tide array beam means that you've created sensitivity to a very focused patch of the sky. So for example, there's some nice simulations here by some of our engineers. If you look at this top right corner, often for pulsar astronomy, it's not even necessary to use the full array. So here is the distribution of the full array's antennas. Here we're just picking the central 1 kilometer core, and the associated tide array beam has got a full half width maximum power of about 0.5 arc minutes, I'd say. And similarly, if you're using the full array, you can see the beam shape is slightly larger, but you can see that it's very well focused to the innermost part. So this type of setup is ideal for observing point sources like pulsars, because you're not really interested in creating spatial resolution on the sky. So in this paper by Colgate et al. On the SKO, they've got this nice graphic just showing how do we, what are the different ways in which we can use interferometers. And so you're quite familiar with the idea that a single dish will have its associated beam pattern. You can have an interferometer, combine that and have the sort of incoherent combination, which will have a larger field of view. Or you can do what we're doing here and make sure you're adding all the emission coherently, such that you've caused this very focused and narrow tide array beam. So in this particular graphic, they're showing an instrument that's formed 3 beams on the sky. So for most of today's talk, we'll only be talking about MeerKAT producing a single beam, but it is in the current commissioning phase of producing up to 4 steerable beams. And so this is ideal for looking at faint point-like sources such as pulsars. Okay, so where does this beamforming process fit into the signal chain that you might already be quite familiar with? So just recall from your interferometry lessons that the MeerKAT correlator will produce frequency channelized complex voltages, and it will do so for each polarization, right? So these products produced by the interferometry correlator are then calibrated through the calibration process we discussed, and finally received by the beamformer, which will do the addition of these signals. And it will have to do so for each polarization stream independently again. So here is just a summation showing that we're adding the complex voltages over each antenna to form an output voltage. And it's here where I want to pause to say that you kind of have choices of how you go ahead. So earlier beamformers, maybe from about a decade ago, would at this point have said, okay, I have the calibrated signal, I've added them all coherently in phase, I'm going to square law detect them now and have powers come out. But the more modern day interferometers, such as MeerKAT, will delay this this process of square law detection just a little bit to actually use the phase information. And it's here that we're going to have to do our little interlude back into the interstellar medium, because the reason you keep the phase information alive in the beamformer for a little while longer is because you will actually use that. You will do a correction. You will do a correction in the phase domain, as I'll show you hereafter, and that correction we call coherent de-dispersion. And after you've applied coherent de-dispersion, well, then you'll be okay with letting go of that information. So now let me explain to you why and what is this coherent de-dispersion, why do we need it, and that is exactly the interlude to the interstellar medium. Okay, so we're back in the far field, we're back in the world of astronomy and astrophysics, And the interstellar medium is, well, it's this medium between all the stars and other objects within our galaxy. And you'll learn from our next pulsar lessons that, and the reasons will become more clear then, that most of the pulsars that we observe are within our own galaxy, within the Milky Way. We are starting to observe them outside. So there's a couple already known for a while in the Magellanic Clouds, because that's still quite close by and easy to find. And it is the FAST telescope's goal to ultimately detect pulsars in Andromeda, but we're not there yet. And so the medium between pulsars, which are going to be the main signal for time domain astronomy, and the observer is mostly going to be the interstellar medium of our own galaxy, of the Milky Way. And this interstellar medium, well, it's a diffuse gas, and it has the typical properties you expect of a gas. So a gas is mostly defined by its state of ionization. So either it will be very hot and fully ionized and full of free electrons, or it will be in a sort of a colder state in its atomic and molecular state. And then there's also more macroscopic particles to the ISM, which are dust and other tiny solid particles. So for radio waves in particular, because we're now hoping to observe a radio emission from our rapid time domain transients, the propagation of the radio waves through the interstellar medium will mainly be affected by what we call the sort of ionized ISM, or the cold plasma component, or other people call it the WIM, the warm interstellar medium. And all these words, warm and cold, are really trying just to say that it's not hot, meaning it's not the fully ionized part of the ISM, so it's not the H2 regions, and nor is it a lot colder because we need the free electrons. So it's partially ionized plasma, which has a temperature of about 8,000 Kelvin. And the main takeaway message here is that the way in which I characterize this ISM is through understanding its electron density content. So if you look at this image I've got up here, so this is a model of the electron densities in the plane of our own galaxy. Okay, so you can clearly see the spiral arms here. You can see that the highest electron density that we measure is kind of in this torus around the center, and those highest values are about 0.2 per cubic centimeter. And then the rest of the electron densities kind of trace out the spiral arms, and more typical values are sort of less than 0.1 per cubic centimeter. And so you will be facing a varying amount of electrons depending on where you are pointing your telescope. And this will become relevant to sort of the guts of the beamformer. Okay, so the interstellar medium, like all media in physics, has an associative refractive index. And in particular, this refractive index relates to the plasma's resonant frequency. So it's this nu p. And it will also depend upon the observing frequency. So the frequency of the radio wave or the emission that's trying to propagate through this interstellar medium. So I just want to dial back to your optic lectures that you may recall from undergraduate. So there we defined the refractive index via Snell's law, and that was often defined through the symbol n, and it just gives the ratio between the speed of light, so sort of the ideal propagating speed, with respect to or over the altered speed of the waves in that particular medium. So let's say the speed of light in water, if it's moving from vacuum to water. Now, in ISM physics, we tend to define the inverse refractive index that is labeled by mu, and we also just call it the refractive index. So in case that causes confusion, they are reciprocals of one another, but they describe the same process. So this ISM refractive index mu is, as I said before, a function of the resonant plasma frequency of the ISM. So it's the plasma has its own sort of natural frequency at which it resonates, nu p, and the frequency nu of the radio waves or the emission that's trying to propagate through this ISM. Now, the resonant frequency of the ISM, well, that will be defined by the things that characterize it. And you'll recall from that spiral diagram that the resonant plasma frequency is defined by electron densities. And so it's understandable that this frequency will be made out of quantities that relate to electron values. So you've got the electron mass in there. You've got the electron charge up here, and you've got the electron mass down here. And then you've got this electron density value. So if we just look at what would be typical values for this frequency of the medium that our time domain signals have to propagate through, well, we've got the mass and charge as constant, so we can just plug them in, and we see that this resonant plasma frequency will be sort of order kilohertz, depending on what this exact electron density is. And from that spiral, sort of the average across galaxy electron density is about 0.03. And so if we just plug that in, well, then our interstellar medium has got a plasma frequency of about 1.5 kilohertz. So the question is now, will my radio waves make it through this plasma? And so we can think of the radio waves that I'm going to try and observe to have some group velocity Vg. And the ISM refractive index can now obviously just again be written as a ratio of these two speeds, the speed with which the waves are propagating through the ISM and the fastest speed of light. And plugging in back the quantities that we've seen before, we've got this expression. And so the radio waves with group velocity Vg, well, they will propagate as long as their associated frequency is larger than the resonant plasma frequency, because, well, then the square root is real, positive and real. If it's the other way around, then this becomes imaginary, and that's sort of the mathematical way of saying physically these waves won't be able to propagate through the ISM. So, of course, if this is the requirement, we can see that our radio waves will propagate through the interstellar medium, no problem. They're going to have frequencies 10 megahertz up to 100 gigahertz, a massive spread in radio wave emission, as you've learned already. And that's even at its lowest boundary, that's always much, much, much larger than this 1.4 kilohertz. So, through this process, we've now learned that the radio waves coming from, for example, pulsar signals, they will propagate through the interstellar medium. That's not a problem. But by how much will their velocity actually change? So I can expand this just using a standard Taylor expansion. I've just written it up here to sort of the first two terms. And now you can ask some basic questions just staring at this, at the mathematical properties of this equation. And it's clear that, well, if the waves that are trying to propagate have an infinitely large frequency, well, then this goes to zero. And so the speed at which they propagate is just the speed of light. But obviously, the lower this observing frequency becomes, the more this will have some sort of impact, and you will be, the waves will be traveling at a speed that's just somewhat less than the speed of light. And the obvious question next to ask is, well, what are the numbers? And I can see my time, so I'm just going to try and speed up this discussion a little bit. It's a pretty simple computation. You can explicitly compute by how much there is a delay between the signals needing to travel through the ISM and what it would be like if they had just traveled with the speed of light. Okay, so this is the bit that we need to compute. This is how long will it take at the speed of their group velocity. And you've already seen that that is, again, a function of these frequencies, the plasmas and the propagating waves frequencies. And plugging in all the equations that you've already seen, the only bit that you can't drag out of the integral is this last remaining bit where we have to integrate over the electron densities from myself to wherever the source is. And as you've seen in that spiral arm model, well, this is not necessarily constant everywhere. This depends on where I'm looking at. And so the things that we can plug units in for, we plug in and we kind of get sort of 1,000 seconds out here, but we still have to scale that by frequency -2. So that will become a lot less soon. But here, what I want you to notice is that we call this quantity here the integrated electron density from myself to the observing source. That we call the dispersion measure. And it's got units parsec per cubic centimeter. And this delay caused by the ISM, well, that has a strong frequency dependence, as you can see there, with the -2 power. Okay, so typical values is, well, let me plug in, I'm observing at 1,000 megahertz at, say, 1 gigahertz. If I plug that in, then I see the delay caused by the ISM is a couple of milliseconds times whatever this dispersion measure is. And no matter where you look in the galaxy, the dispersion measure is typically going to be somewhere between 100 and 1,000. And so immediately what you see is the delay caused by the ISM, well, that's just going to be at most a second. So you can start to see how the delays imparted by the ISM, well, I mean, they've got little consequence on other fields of astronomy. If you're imaging, you don't care that there was a second delay between, or even less than a second delay between some components within your signal. But if you're trying to understand what's happening to a source at sort of sub-second timescales, well, then this clearly will become important. And also, if your source is actually emitting, as it will do, at more than one frequency, well, then the delay will be different for the frequency of the emission propagating through the ISM. And so all of a sudden, you're in the situation where the highest component of your signal will arrive first at your telescope, and then a little later, the lower frequencies will arrive. And again, these delays are very short, maybe only a second, but that's sort of the time resolution about which we exactly care. Okay, so recall that this interlude was sort of a deep breath to just get us back to the last bit of what does my beamformer do. And so the reason we held on to that phase information was because the delay imparted by the ISM, that can be thought of as imparting a phase change on the radio waves. And so we can correct that phase change in the Fourier domain simply by multiplying the inverse of whatever the ISM caused on our intrinsic electric field. So let's say this here is the intrinsic electric field, and then the ISM will act to cause a phase change on that, so that when we actually measure the electric field at our telescope and the voltages that it induces, well, then that will be, will have this ISM property baked into it. But if we know what that phase change is, because we know where we're observing and what the dispersion is, well, then we can just correct it by multiplying it with the sort of the inverse phase correcting function. And that's exactly what we do in the beamformer. We point to a source where we know what this expected phase change is going to be. And so per frequency channel and per polarization, we correct for this. And once it's corrected for, this is the process of coherent de-dispersion, well, then you'll have your signal arrive at all frequencies at the same time. Okay, so that was the interlude. So let's just quickly go back to our schematic of the signal chain and have a look at where this process fit in. So after we have received the calibrated signals and added them to produce a single output voltage at the beamformer, we've hung on to the phase information for a little while so that we can do this coherent de-dispersion. And then as soon as that's done, we can do the square law detection of our signals. Okay. And this here was a zoom in because I know sometimes the resolution isn't great, but it just shows that in this schematic illustration, indeed, what it's trying to show is that for each frequency channel, we get rid of the delay imparted by the ISM. All right. Okay, so one way in which we can actually test, our whole aim was to create this coherent in-phase array with a tide array beam. And one way in which we can test whether we have succeeded in doing so is we can conduct an experiment to see how the intensity of astrophysical signal is changing with the increase of number of antennas. So I think in Ben's lecture already, he alluded to this idea that if you are adding signals coherently or in phase, well, then you expect these signals to scale linearly with the number of antennas. However, if you only added them incoherently, then they'll only scale with the square root of the number of antennas. So this is sort of a commissioning exercise where if you look at a pulsar, in particular here we looked at J1056 minus 6258, you pick a pulsar that's flux stable, so you know that the source that you're looking at is not going to change its own intensity, and you check that you have, after you've done those two calibration steps, you check that the resulting beam is of such nature that if you change the number of antennas, well, then the intensity of the signal, intensity of the astrophysical object you're observing is just scaling linearly. And so we see that MeerKAT's doing that really well. And here on the right-hand side, a similar idea, but here from simulations, just showing if I change the number of antennas in my array, going from 2 here, so you can see that classic gradient pattern, up to 16 antennas. So this was the old days when MeerKAT only had 16 operational antennas. Well, you can see that the sort of tight tide array beam has been formed. We will just have a look at this, what I call precision timing support for the Beamformer. So understanding the ISM, which has less than second time delays, and you'll learn in the next lecture the understanding the astrophysical objects of interest who can spin at tens of milliseconds. We need to know that the time stamps that we are imparting to our data at MeerKAT is accurate for this type of science. And so how do we go about that? So I think Ben again also mentioned the masers that we have on site. So we've got 2 maser clocks on site, so 2 hydrogen maser atomic clocks. I am told that they are hosted in a building for which the temperature is controlled to not go higher or lower by 0.3 degrees, so in a stable environment. And these atomic clocks, they produce for us what we call Kourou telescope time, so a time standard right there at the telescope. And then basically to ensure that this time standard is good, we keep on tracking by how much this local time standard is changing with respect to the UTC standard. So that's done through satellite communication, and the UTC time standard that we're referring to is the South African local one that's maintained by the Meteorology Institute of South Africa. So we can, at any given time, basically, the masers are of such stable nature that at any given time, we're confident that this Kourou telescope time is already lying to within 20 nanoseconds of the UTC standard from NIMSA. So any timestamp that's imparted to the data at that point will already have this sort of high accuracy. But then for pulsar timing, we invoke what we call these precise sync epochs. And so these are corrections to this already high standard of precision to make sure that we can bring it down to less than 10 nanoseconds. And so how do we create these precise sync epochs? So the idea is the following. You basically use your system to time itself. So the masers are producing a pulse on site, and then they observe how that pulse travels through the full signal chain until they reach the digitizer. And through this process of tracking the pulse going through the whole system, you can observe the delays within your system. And the basic origins of where you expect some delays to enter the system is things you've learned about before. So there are the geometric delays, which are probably reasonably well understood. And then there's all the delays within the antennas, within the receivers, the cables that take it to the digitizer, and then the digitization itself and the F engine. These can all impart small delays on the signal. And the idea is that by producing your own on-site pulse and tracking how that moves through the system, you know how your system, by how much signals are typically delayed. And here, just as a sort of a proof of concept that this precise time manager works, what we've done here is we've run all our calibrations to form the phased array. So here I'm just showing that band pass shape again, and so you can see the band passes are nicely aligned as sort of one measure of having performed full beam calibration. And we run the precise time management system before the calibration was applied and after the calibration is applied. So we know that the calibration will basically correct the delays in the system through the calibration procedure up to only having delays of about less than 2 nanoseconds. And we see that our precise time management or monitoring system measures that same change in delays. And so we know that it is accurately reporting delays within our system. And this continuous measuring of delays in the system when conducting pulsar timing experiments, those are used to produce these precise sync epochs that we then use to retrospectively slightly correct the timestamps on data sets if need be. Okay, so here I wanted to show you sort of in live the MeerKAT backend in action. So let me start this video. I can always pause it again. So here I'm just clicking on the sort of the progress output. When Ruby introduced you to the archive, she showed you that this whole script log is available to you after the fact as well. So let me pause here. So nothing much has happened. We're still waiting for things. Let's see. Okay, waiting for an external machine to get ready as a target. So there we go. PTU's target is 0437, so that's the pulsar we're going to observe, and it will track to it. And just above this, you can see that it's printed out, got precise time reading. So it's activating this precise time measurement system. And now I'll go to the diagnostic output of the pulsar backend machine. So this video here is sped up by 20 times. So that's why the signal to noise ratio of this pulsar is increasing so rapidly. But what you see here, I've just paused the video for a moment, is we're observing a pulsar. This is the pulse profile. Because the pulsar is known, we could apply this coherent dispersion. So here is the plot of what the pulsar looks like in frequency. And you can see clearly the pulse, all of the frequencies are arriving at the same time. So there's no sort of smear or delay because we've got a good idea of what the electron content looks like up to that pulsar. So in lifetime, we can kind of fold the signal on top of one another and get these bright pulse shapes out. And this is just what the pulsar looks like in time. This is probably where the observation started and the data streaming wasn't 100% yet. So the MeerKAT telescope will point at one pulsar, and then depending on what's in the queue, it will jump to the next pulsar and start the same. And you can see how the signal to noise ratio for the particular pulse signal is increasing with time. Recall that we expect that from the radiometer equation to go basically as the square root of time. And so if you observe long enough, then this is sort of a square root of that. Okay, so this is indeed the very last slide where I just wanted to again say that in this lecture, basically, we focused on how do we form the single tide array beam that I know all the signals from my various antennas are being added in phase, referenced to this phase array center, and then how do I point this to a compact source like a pulsar. Now, and in particular, we also looked at this idea of coherent de-dispersion. So how do I get rid of the ISM impact if I know the pulsar well? So that is kind of one of the most used setups of the MeerKAT telescope for doing time domain astronomy. But in this last slide, I just wanted to introduce this idea of flexibility. So while we don't really need the long baselines to get high spatial resolution, and we don't benefit from that design of the interferometer, we do benefit from its flexibility. So for example, one thing that we can do that's really cool is we can do multiple subarrays. So you can split your group of antennas into two, and you can have half of them observe a pulsar at, let's say, L-band frequencies, while the other half is observing at U-band. And so you are basically simultaneously getting a much broader frequency range data set. And also, you can fiddle a bit with the sort of time and frequency resolution. So for pulsar timing work, we tend to reduce the frequency resolution. So we'll only take like 1024 frequency channels, but that ups the time resolution. So depending on the different modes, the beamformer can record time resolutions of up to 38 microseconds, depending on what machine is running. And probably even faster in some of the Frapham USE machines that Ben will be telling you about. And to end, so this is really going into what Ben will be talking about later, much of, especially this last backend output that I showed you, well, that relies on having, looking at known pulsars. But what if you want to find new pulsars? And so then you do all sorts of other interesting stuff and form multiple beams on the sky so you can scan and search quickly. And programs such as Trapham are very involved in that. So these are the websites of the two main pulsar and time domain projects on MeerKAT. So just have a look there if you want more information.